So I'm presuming that most of you are familiar with the idea of a flow net, but in case you aren't, we will quickly spend a couple of minutes just talking about it, and then we'll move on. Okay. So Raish, you can do one thing. You can keep the room at mute, and if somebody has a question, unmute and then speak, because I get a little bit of a echo. Is that okay? Maybe even I can mute you.
Yes, sir.
Yeah. I have muted you guys. So if ever there's a question, you'll have to, I can unmute because I can see you guys, but when I present, it becomes difficult to see. But anyway, all right. So let's get started. So today we'll talk about flow nets. But before we get into flow nets, we will solve one particular problem. I mean, not so much solving, but just thinking about how to solve this, and then this becomes the basis for us to start talking about flow nets. So just take a look at this problem statement. 3 observation wells are installed to determine the direction of groundwater movement and the hydraulic gradient in a regional aquifer as shown below. Estimate the groundwater flow direction. So now it's a direct question, and the only answer that you're expected to give is not a qualitative answer. What you're expected to say is the flow is happening in this particular direction, whatever the direction may be. Okay, so you see there are 3 wells. We are not going to get into quantifying the answer for this particular problem. We will talk about it more from a general idea of how to solve it. Okay, I'm not going to do it precisely. I'm going to do it to indicate the way you would solve a problem of this nature. Okay, yeah. So take a look at this. I have well 1 where the water level is at an elevation of 32.55 meters with respect to some datum. Well 2 is at an elevation of 32.41 meters with respect to some datum, and then well 3 is at an elevation of 32.66 meters with respect to the same datum. Okay, and the distances between wells 1, 2, and 3 are given to us. Okay, so now the question is, how do I figure out what direction the water is moving? What is the amount of information provided to us sufficient to figure out the direction of movement of water? That's the first question. Is this information sufficient? We solved something similar in a class probably 3-4 weeks back, but I gave a different context to it. There's some contamination, it's moving towards your house, something like that. Okay, the idea is the same. It's just the setup of the problem was a little bit different then. The setup is slightly different now. Anybody would like to volunteer? Can't see faces very clearly, but I can guess who's sitting. I can see Anvesha, and then there's Alina and Purnima, correct? Okay, put a thumbs up if it's 2 of you. Okay, great. And then there is Vignesh, I think, and Manish. Super. And Raish, of course. Okay, not bad. And Deepshika is joining in online. Okay. So what we do is, we know that the elevations, well 3 has got the highest elevation, and well 1 or 2, which one is lower? Well 1 is at 32.55, in between 32.66 and 32.41. So well 2 is at the lowest elevation. So one way of thinking about the flow direction is to say water goes from high head to low head. So it must be going from 3 towards 2, and from 3 towards 1, and then from 1 towards 2. So if you just had these 2 points, if you had any 2 pair of points, you would say the flow is going from, let us say you had only 1 and 2. If you did not have well number 3, you would say the flow is going from well 1 towards well 2, right? So this would be the flow direction that you would give if you did not have well 3. If you had only well 1 and well 3, then you would say this is the flow direction, right? Because 32.66 is higher, 32.55 is lower, right? If you only had well 2 and 3, then you would say this is the flow direction, right? But now, unfortunately, these three directions, look at them, they are so different. Obviously, only one of them can be right, or none of them are right, or there is some other third answer which we don't know at this point in time. Sorry, there's a fourth answer that we don't know at this point in time. So what can we do? Come on, quickly, anybody. You want me to unmute? I can unmute. Quickly. Soumya is here. Tanvi, anybody? Okay, so can we do this? If 32.66 is the highest and 32.41 is the lowest, somewhere between well 2 and well 3, the head will be 32.55, right? The head which is there at well number 1, 32.55 will be somewhere in between well 2 and well 3, because from 0.66 to 0.41, somewhere in between will be let's say somewhere over here. That is the location where the head would be 32.55, somewhere in between. Actually, closer to where? What's the midpoint between the two? 12.5. It would be closer to, anyway. So somewhere here would be 32.55. Agreed? And if these 2 points are at the same elevation, then you can draw an equipotential line. An equipotential line is basically a line that connects 2 points that have the same total head, right? And once I know the equipotential line, I can figure out that the flow will be, sorry. Yeah, I'm having a lot of trouble with this. I've tried to minimize using the, anyway. Right, so the flow will be at right angles to the equipotential line. So this idea that if I know the equipotential line, then I can infer what the flow direction will be, as the equipotential line and the flow line or the stream line will always be perpendicular to each other, right? This is the fundamental idea which we are going to take forward when we talk about flow nets. Okay, so all the other three directions that I spoke about, none of them are right. Right, of course, this one was kind of close to the correct answer, but it's not perfectly correct. So the actual flow direction will be, right, so the actual flow direction will be somewhat like, of course, given that the distances are provided, it's always possible for you to figure out exact location where this 32.55 will be, and then draw a line connecting those two, and then draw a line perpendicular to that. That's possible. Okay, so now, given this background, let us take a look at the idea of a flow net. Okay, now a flow net is basically um, a pictorial representation of different equipotential lines and different flow lines which are orthogonal to these equipotential lines. Now, what is typically done is that these equipotential lines are usually spaced at a uniform interval apart. When I say interval, I don't mean the spatial distance between them, I mean the head difference between them. Okay, so for example, I have an equipotential line here corresponding to a head of small h. The next line, the one over here, is at a potential of h minus dh. Okay, now the next line will be h minus 2 times dh, right, and then so on. So therefore, typically, the equipotential lines are always, , 2 , 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 the difference between any two consecutive equipotential lines, the difference in heads between them will always be, we try to maintain it, not try to maintain it, it's always maintained equal. I'm not saying that the distance between, the physical distance between those two lines is the same. I'm saying the head difference between two successive equipotential lines is maintained the same way. So for example, if small h is 10 meters, and then h minus dh, the next one is 9 meters, then the next line will be 8 meters, 7, 6, 5, 4, 3, 2, and so on. Okay. It is not necessary that the distance between 10 and 9 is the same as the distance between 9 and 8 and so on. That would be very nice, but it's not necessary. It's not a necessary condition. Okay. And then similarly, I have these flow lines, which will always be perpendicular or orthogonal to these equipotential lines. Wherever they cross, wherever these two cross, it will be at right angles. Okay. Now, one more aspect of that's important is that between any two successive flow lines, the flow is always, the flow can never cut across these flow lines. Okay. So which means that flow can never go like this. This is not possible. Flow can only go parallel to the streamlines. It can never go at any other angle. Okay. So what I'm trying to say is this is not possible. Okay. All right. So these flow lines are basically, you can think of them as a no flow boundary. A flow line can also be thought of as a no flow boundary. Now this becomes important. What do I mean by no flow boundary? No flow boundary means that there's no gradient across these flow lines, which makes sense, right? Because if you look at this point, if you look at any point, okay, so what will the gradient at this point be? In the direction perpendicular to the flow? In the direction perpendicular to the flow, yeah, maybe you should be in unmuted stage, because the silence is really killing the joy. Yeah, Raish, can you please unmute the, I can handle the little bit of an echo. Thank you. You can just leave the microphone in a place and then hand it around if necessary. All right. So at any one of these points where I've drawn an X at the flow line that intersects the equipotential line. Right. So the gradient in the direction perpendicular to that will be, perpendicular to the flow line will be, what will the gradient be in the direction perpendicular to the flow line? Zero. Why will it be zero? Okay. I can't hear very clear. Can't hear a word. Okay, maybe just hold it a little bit far from you while speaking.
That line.
Okay, there's an equipotential line, which means the head along that line is equal. So if I take the gradient in that direction, the gradient is going to be zero, because perpendicular to the flow line is an equipotential line. The potential does not vary in that direction, so there's no gradient possible. So the only possible gradient is in the direction perpendicular to the flow line. Oh, sorry, perpendicular to the equipotential line. Okay, so let's just keep that in mind. Now, if I were to write, now in between these two flow lines, I've written dq, or there's a dq over there. So if I want to find out what dq is, it'll be dq is k, the hydraulic conductivity in this region, multiplied by the gradient, and the gradient will be dh, the difference between any two successive equipotential lines, and ds, which is the distance between two successive equipotential lines, right? So that's dq. Okay, now suppose I want to find the flow rate per unit cross section area. That's dq. If I want to know the total flow rate, then it would be k times dh by ds multiplied by dm, which is the width between two flow lines, assuming some kind of unit thickness in the direction perpendicular to the screen. Okay, everybody agrees with this? dq equal to k times dh by ds times dm. Okay, now suppose I were to do this task in a very careful manner, in such a way that I have a square kind of flow net. Now this is a flow net. Basically, I have a series of equipotential lines and a bunch of flow lines which are orthogonal to these equipotential lines. The resulting representation is what we refer to as a flow net, because it looks like a net. There's squares and so on, right? There's squares that are created between the equipotential lines and the flow lines. Now, in the extreme case, if I have square flow nets, okay, if you have an ideal situation where the distance ds is equal to the distance dm, this is something that is in my control as a person who's creating the flow net. I can attempt to get ds equal to dm. Then I get a simple expression dq equal to k times dh. Okay, so which means just by looking at these equipotential lines and by knowing the hydraulic conductivity in that region, I can figure out how much flow is happening per unit thickness, right? So that's a powerful visual representation where observing the equipotential lines and the flow lines produced, I'm able to figure out how much water must be flowing in this particular region just by knowing the hydraulic conductivity and these equipotential lines and the corresponding flow lines. Okay. All right. So we will take a more concrete example. We can try and achieve this. So let us say I have a series of equipotential lines. So I'm numbering them H0, H1, H2 up to Hn, let's say. Okay, so you have these dashed lines or dotted lines which correspond to my equipotential lines. I'm numbering them from H0 all the way to Hn. So H0, H1, H2, and so on. Now, along with these, I have my flow lines, which are always going to be orthogonal to these equipotential lines. And I'm numbering them. Okay, I've numbered them from 1 to m, but let's assume that that's also 0 to m. Okay, so 0, 1, 2, 3, 4, all the way to small m. Okay, so in between every two pair of successive flow lines, I have some flow, dq1, dq2, and so on up to dqm. Okay, so if I number it from 0 to m, I'll get m number of dqs. Okay. Anyway, all right, so far so good. Everybody is in agreement with what we have so far. I have n plus 1 number of equipotential lines, numbering from H0, H1 to Hn, and m plus 1, m as in Mary, m plus 1 number of flow lines, numbered from 0, 1, 2, 3, all the way up to m. And in between every two successive pair of flow lines, I have the flow rate, an infinitesimal flow rate. Let's call it dq1, dq2, up to dqm. Okay, so now if the spacing between each head contour is uniform, then I can write the head difference between any two successive head contours, dh, as hn minus h0 divided by n, the total number of jumps that I'm taking. So h0 to h1 is one jump, h1 to h2 is the second jump, and so on. So hn plus 1, hn minus 1 to hn will be the nth jump. Okay, so if each jump is of the same size, then the size of the jump dh is simply hn minus h0 divided by the total number of jumps. Agreed? right? So now let us refer to this Hn minus H naught, the total head difference between the last equipotential line and the first equipotential line. Let us refer to that as capital H. And N, of course, is the number of jumps that I'm taking between each successive, equipotential line. Okay, it turns out that I don't have a watch with me or my mobile phone, and I don't know what time it is. So in case I'm going over time, somebody can please just let me know. Okay, I know it's probably been 20-25 minutes or so, but let's see. All right, so far so good. DH, the head difference between any two successive equipotential lines, is capital H divided by small n. Okay, so now the total flow Q caused by these n number of equipotential lines and m number of flow lines, sorry, m plus 1 number of flow lines, is m times d cube, and dq, like we saw in the previous slide, is k times dh, right? Just go back a couple of slides. dq is k times dh, right? So extending that, can we not say that q equal to m multiplied by k into dh? And what is dh? It is capital H by n. So I get this nice and simple expression, q equal to m times capital K, the hydraulic conductivity in this region, assuming that it's not changing as a function of space, times capital H, which is the difference between the last equipotential line and the first equipotential line, and n is the total number of equipotential lines, right? So if I give you a flow net of a particular region, and I tell you what the hydraulic conductivity in that region is, just by finding the difference between the first and last equipotential lines, and by counting the number of flow lines and the number of equipotential lines, which is small m and small n respectively, I can figure out how much flow is happening in this particular region. Now that's a powerful tool, right? That what requires a lot of course, constructing a flow net is not an easy task. But suppose I have a flow net available, then I can use this simple formula to estimate how much flow is happening through that particular region. Any questions?
Any question, sir?
Okay, no questions. All right. Thank you. Now let's move on. Let's now let's take a look at a slightly different scenario. Now the previous scenario, in such a way that the distance between every two successive head contours is the same. The distance between every two successive flow lines is the same. So it's a square flow net basically. So if I have a square flow net, I have this very simple illustration. But suppose I don't have a square flow net. I have something that looks a little bit more complicated. Okay, now take a look at this, for example. Okay, you see some numbers there, 360, 358, 356, 354. All of those are numbers, and those are basically 2-meter contours of the groundwater surface, right? So when I say 2-meter contours, that means that the difference between any two successive contours is 2 meters, right? So so I have a 350-meter contour and a 348-meter contour, right? Now the distance between the 350 and 348-meter contour need not be the same as the distance between the 348 and 346-meter contour. Okay, so I'm going to put you back on mute because the echo is a little disturbing. Sorry. Okay. Now remember what we said about. Now, unfortunately, up to now we were using dashed line to refer to equipotential lines and solid lines to refer to flow lines. Now, in this particular figure, they've done the opposite. So the solid lines are the equipotential lines, and the dashed lines are the flow lines. Okay, there's nothing complicated about it. We just kind of swapped the system. Okay. Anyway, Now, remember what we said about these flow lines being no flow boundaries, which means whatever flow enters here, okay, between those two successive flow lines, the flow coming out here has got to be the same as that. Do you agree with that? No additional flow can enter into the system between these two flow lines, unless there is a specific situation, but we'll not talk about that. In this particular case, for example, whatever flow is coming in at that first cross section, when you go to the second cross section, the quantum of flow cannot be different, although the spacing between the different contours and the flow lines is not being maintained at a uniform rate. Okay, so what is causing this change in the spacing of the contours, and what is causing the width between the two flow lines to not remain the same? One possibility is that there is some additional water getting into the system. Unless, if that is not happening, let us assume for a minute that there is no additional water entering into the system between these two cross sections. Let's say cross section 1 and cross section 2. So cross section 1 is around 354, 352 meters, and this cross section 2 is at 348, 346 meters with respect to the datum, right? What I'm saying is that the flow coming into cross section 1 is about the same as the flow going out of cross section 2. But the question is, why is the width between the flow lines W1, for example, not remaining the same? Why is W1 and W2? Why are W1 and W2 different? Or why is the distance between two successive contours, why is it increasing? So for instance, between 354 and 352, there is a very short distance, but between 348 and 346, there is a greater distance. What could explain that? That is the question. We'll try to answer that. Okay. Assuming that there's no additional flow coming into this particular system, can we say this? I've written the total flow between these two contours, Q, it's W1 times Q1, which must be equal to W2 times Q2. Okay. When I say Q1 and Q2, I mean the Darcy flux. Okay. And W1 is the width. Let's assume some kind of unit thickness in the direction perpendicular to the screen. Okay. Is that all right? So W1 Q1 equal to W2 Q2. Now, how do I find Q1 and Q2? Can I say that Q1 is K1 times I1? K1 is the hydraulic conductivity in region 1 multiplied by the gradient in region 1, which must be equal to W2 times K2 times I2. Can I say that? So Q1 is K1 times I1 and Q2 is K2 times I2. Now, going by this equation, I can simply insert those in there. I get W1 times K1 times I1 equal to W2 times K2 times I2, which if I rearrange, I get this interesting expression, K1 by K2 equal to W2 by W1 into I2 by I1. Okay, I've just rearranged the terms a little bit. Now, suppose W1 and W2 are about the same. Okay, suppose W1 and W2 are very close to each other, like, or let's say they are even exactly equal, right? Then I get this interesting expression that says K1 by K2, since W2 and W1 are equal, they just go away. I'm left with this expression K1 by K2 equal to I2 by I1. Now, what does this tell you? What do you think this is telling us? That the ratio of the hydraulic conductivities between region 1 and 2 is kind of inversely proportional to the ratio of the hydraulic gradients at 1 and 2. So I could write it as 1 by I1 by I2, right? So it's inversely proportional to the ratio of I1 by I2. K1 by K2 is inversely proportional to I1 by I2. What does that mean? What does that mean? Or maybe I'll ask it like this. If K1 is greater than K2, if K1 is greater than K2, then what can you infer? Or in this, okay, in this case, we have, which is greater, I1 or I2 in this case? Okay, what is I1, first of all? I1 is the difference dH by ds. dH is the same in region 1 and region 2 because the contours are spaced 2 meters apart, right? I mean, the head contours have a difference of 2 meters. Right? Yeah, go ahead if there's a question.
Sir.
Yeah,
No, sir. No question.
no question. Okay. So I1 will be the difference between, let's say, 352 and 350, that's 2, divided by the distance between the 352 and the 350 contour. Right? So that distance is, let us say, some distance ds1. And then when you come to I2, the gradient in region 2, 348 minus 346, the numerator is the same, 2 meters. But the distance between 348 and 346 is larger than the distance between 354 and 352. Right? Okay. So I2 is 2 meters divided by the distance between the contours. And I1 is also 2 meters divided by the distance between the contours. Which one is larger, I2 or I1? Which one is larger? I2, the denominator is larger. I1 compared to I2, the denominator is smaller. The numerator is 2 meters in both cases. Yeah, unfortunately, I'm not able to hear what you're saying. Either the microphone, the battery is dead or something like that. Sorry, I can't hear.
Yes, sir. Dome is larger than I is less.
Huh. Say that again.
Uh, I is less.
I'm having a hard time understanding what you said. It's not clear. Audio is totally not clear. Can you come closer to the podium, maybe, because once you move far away, I think the reception is not so good. Sorry about this. Okay. So I1 is 2 meters divided by the distance between the contours. I2 is 2 meters divided by the distance between the contours. The denominator for I1 is smaller than the denominator for I2. So I1 will be smaller than I2. Correct? The gradient is larger at location 2. Hydraulic gradient is smaller. I'm sorry. The hydraulic gradient is smaller at region 2 compared to the hydraulic gradient at region 1. Which means, which is greater, K1 or K2? If you put up your right hand, it means K1 is greater. If you put up your left hand, that means K2 is greater. I can't see everybody, but I can see 4 people. If you put up your right hand, that means K1 is greater than K2. If you put up your left hand, that means K2 is greater than K1. You'll have to really put it up well, Purnima. Thank you. Vignesh, right or left? Left. Everybody's left. That is correct. K2 is greater than K1, which means in a region where I can't see you, Manish, I'm sorry. So in a region where the hydraulic conductivity is larger, the contours will be spaced farther apart. In a region where the hydraulic conductivity is lower, the contours will also be close to each other. Okay, so now this is the inference that we can draw from this particular, just by looking at a head contour, a flow net, you can infer that in this region, the hydraulic conductivity will be higher, in this region, the hydraulic conductivity will be lower, and so on. If the contours are close to each other, hydraulic conductivity is low. If the contours are far away from each other, hydraulic conductivity is high. That's the rule. Fairly simple, right? So this is something that that you can, if I show a flow net to anybody, just by looking at it, you should be able to infer where the hydraulic conductivity is higher and where it's lower. Now, please remember that if there is an external source of water or an external sink which is removing water, this rule doesn't quite apply so straightforward, because then you are causing the head to change rapidly because maybe there's a well or something like that. So if there are no external sources or sinks, then what I said is pretty much true. Okay. High conductivity contours have a greater distance between them. Low conductivity contours are close to each other. That is the general rule. Okay. All right. So let's move on now. Now, you can also use this whatever we've discussed now to actually estimate the transmissivity of an aquifer. So now let us imagine I have a pumping well which is pumping out some water at some rate Q, let's say. Okay. Now what happens is, around the pumping well, usually I will have what are called closed contours, right? A closed contour. Yes, is there a question? Is there a question, Raish? Somebody put up their hand, or is there a question? It's a yes or no. If there's no question, you can say there's no question. Let's move on. Okay, we'll have to work out the dynamics of the live class a little bit better than this, right? All right. It's okay. Starting trouble. We'll work it out. We'll work it out. All right. So what you see around the pumping well is these closed contours. Okay, when I say closed contour, that indicates that flow is not able to escape out from the impact of pumping. I heard a sir. Is that a call for a question or what? You can shake your head and say, let's move on. Okay, no question. Okay, from now onwards, you all need to come closer to the camera because you're sitting way in the back of the room. Even with my glasses, I can't see that far back. Yeah, it's good. Come to the first row. Because you can see what the camera is focusing on, right? So try to sit in the view of the camera. Super. Yeah, all of this has got to happen before the class starts. Okay. Good. Okay. So everybody agrees or understands this notion of a closed contour. A closed contour indicates that flow is moving towards the well. Okay. A closed contour can also mean that there is an injection well will also create a closed contour, which means that the flow direction is radially outward from an injection well or a source of recharge, let's say. Okay, it could even be recharge can also create closed contours. Okay, so a closed contour is when I have a source or a sink of water. Okay, so now let us say I'm pumping at some rate Q from this pumping well, and if I have these kinds of flow nets or head contours that have been developed for this region, then it is possible for me to estimate what the transmissivity of the aquifer is just by looking at the flow net. Okay, so this flow net diagram is giving me a pictorial representation of how the head is varying in that region in response to this pumping well. Okay, I know what the pumping rate is. I know what the the head contours are. Maybe I have a number of observation wells around this particular pumping well, using which I'm able to come up with this flow net. Okay. And by using this flow net along with the pumping rate, I can estimate what the transmissivity of the aquifer is. Okay, so that's a very interesting application of the idea of a flow net. Okay, so let's see how to do that. So remember our old nomenclature. I have n number of or n plus 1 number of head contours starting from 0, 1, 2, 3 all the way up to n, and the head difference between the last and the first one is capital H, right? So then I came up with this formula. You remember Q equal to Km capital H by N. Okay. Now this was flow per unit thickness of the aquifer. Now let us say the thickness of the aquifer is capital B. Okay. Then I just multiplied by B. I get Q equal to K times M times Hn minus H naught divided by N into B. Okay, B being the thickness of the aquifer perpendicular to the screen. Now remember what I'm showing here is the plan view of an aquifer. Okay, it's not a cross-section view, it's a plan view. So that's why when I say perpendicular to the screen, I mean the thickness of the aquifer. Okay, so if I rearrange this, you get Q equal to K times B becomes my transmissivity P times M, which is the number of flow lines, capital H, which is the difference Hn minus H naught, and then N is the number of head contours. Okay, so if I rearrange this, I'll get T equal to N times Q divided by M times small h. So Q has units of meter cube. Is there a question? No. Okay. So Q has units of meter cube, L cube T minus 1, and capital H, which is the head difference between the last and the first contour, has units of meters, and N and M are just numbers, right? You're counting the number of contours and so on. So I have meter cube per day, or L cube T minus 1 in the numerator, and L or meters denominator. So I'll get meter square per day, or L square T minus 1, as the outcome of this computation, which is the unit for the transmissivity that was. Okay. All right. So let's maybe try to solve one problem. This might be helpful. The figure is not very clear, but the concept is fairly is what we want to focus on. So let's just look at this. The average daily discharge from an aquifer formation in Sparrows Point district of Baltimore, it's a city in the eastern part of the United States, was estimated as 10 power 6 cubic feet per day. Okay, so the Sparrows Point district is this region over here. This region is the Sparrows Point district. Okay, so there are a bunch of pumping wells over here. Okay, I can see 1, 2, 3, 4, 5, about 4 or 5 pumping wells here, and all of them together are pumping around 10 to the power 6, a million cubic feet per day. Okay, a flow net of the region is constructed using available contour lines as shown. Compute the transmissivity of the regional aquifer. So that's the problem statement that we have. So now you will see there are some solid lines with numbers on them. Okay, I think the numbers are 20, 30, 40, 50, 60, and so on. You see those numbers here: 20, 30, 40, 50, 60. Now these numbers most likely are not elevations, these are depth to water level. Okay, because if it was elevation, you can't have elevation increasing towards the pumping well. The pumping well is over here. The pumping wells are over here. The head has to be lowest over there. So as you move towards the well, the heads are supposed to be decreasing, but in this case you see numbers that are increasing: 20, 30, 40, 50, and so on, which indicates to me that these numbers are not elevations, they are the depth to the water table. Okay, but in any case, if the datum is the same, then it really doesn't matter. So I can always figure out what the head difference between any two successive head contours is. Okay, so the first thing I do is to draw these flow lines perpendicular to the head contours. Okay, and then you just count how many flow lines you have, right? So let's do the count. 2, 3, 4, 5, 6. I think there's 15 or 16 lines. So there's 15 in between regions between two successive flow lines, is about 15 of them. Okay. So from the formula that we had in the previous slide, it's n times q divided by m times h. Okay. So n is 4. I have 20, 30, 40, 50, 60. So that's 4 jumps, right? 20 to 30 is 1 jump. 30 to 40, 40 to 50, 50 to 60. So that's 4 jumps. And the pumping rate is 10 to the power 6 feet cube per day. M, the total number that we counted was 15, right? Multiplied by the head difference between the last and the first, 20 and 60. Right? The difference is 40, right? So 40 feet. So then when you put in all those numbers into this equation, you are able to estimate the average transmissivity in this particular region, which happens to be around 6,000 something feet square per day. Okay. Now, remember that this is an approximate way of computing the transmissivity. It's not a very precise estimate, but anyway, our transmissivity numbers are not supposed to be accurate to the third decimal place and so on. They are basically order of magnitude kind of numbers. Okay, we don't really pay attention to it to the extent that is it 6,700 or 6,682? Nobody cares. It's about 6,000 to 7,000. That's the level of accuracy that we typically expect from a transmissivity number. Okay, of course I'm talking about feet square per day. If it was meter square per day, your number would be of a smaller magnitude, right? Because meter square is about what, 10 times smaller than feet square, right? So that's the overall message that I want to be conveyed when we are talking about transmissivities. Don't think it's some kind of a super accurate estimate of what's going on or what the aquifer property is. It is an estimate to help us uh, solve other practical problems. It is not intended to be a super accurate.
So there's a question.
Go ahead.
How did we get 15, the value of M?
It's the gap. Okay, so what is M is the total number of uh, two successive lines. Between them, you have 15 such pairs of streamlines. Because the flow is happening through every two. So it's like if I have 5 fingers, how many gaps do I have in between? 1, 2, 3, 4. So M.
Yes. Flow lines, we need them roughly, or
Say that again. Flow lines.
flow lines that we drew, we made them roughly. So how do we know exactly how many numbers will be there?
No, it doesn't have to be precise. If I draw them closer to each other, right? If I draw them closer to each other, then it won't be a square flow net, more or less. So the whole thing assumes that we are trying to get a square kind of shape to the extent possible. If you make them narrow, it will no longer be that equation that we wrote, k into m by h. What is that? Mkh by n, right? That equation is only applicable if the flow net is square. Okay, we are trying to make it as square as possible, right? Let me just go back to that slide. You will understand what I'm trying to say. So this equation that I wrote, k into m into capital H by n, that is only applicable if the distance between successive, if I go even further back, remember this that I had written. The assumption here is that the spacing between each, so that is fine. Hn minus h naught by n, that is okay. Okay. But I'm doing m multiplied by dq, which means if I know one dq, all I have to do is multiply it by the total number of such dqs. That presumes that the distance between or the dq1 is equal to dq2 is equal to dq3, right? Which again works on the presumption that suppose we have square flow nets. That's where the whole thing started. Okay. Suppose I have square flow nets, then only then can I say dq equal to k times dh. Because only then this ds and dm cancel out here, right? So I'm trying to maintain that. Okay. So this whole thing, yes, there's another question. Is there another question? Yes, no. Oh, time up. Okay. Okay. Yeah. So I'll just stop with this. That the idea is to construct a square flow net so that I can exploit these simple formulas that we have. Okay. If you don't have a square flow net, you can't use that formula. It's not applicable to a non-square flow net. Of course, you will see even this is not a square flow net, but this is about as close as possible to getting a square flow net. Okay. It's not an ideal square flow net. That would be all straight lines and right angles. But this isn't quite that. Okay. All right. Thank you very much. Raish, my suggestion is you try to talk to them and see if you have to replace the batteries on the microphone or something, because there's a lot of, when they speak, I'm not able to hear very clearly. Okay. Thank you. Thank you very much. Oh, Tuesday's class, I would have just landed in Canada. I might not be in a position to teach. So let's meet next Wednesday, which will be Tuesday for me there. Okay, that's okay.
So it's sense.
Yes, Rish.
No, sense. Battery is coming.
Sorry, I can't hear you.
No, battery sense. No battery sense. Hello? Yes, sir.
Okay. Fine. Anyway, it's okay. So there's some issues with the microphone. So, take care, everybody. See you all from Canada next time. Bye.